Hello, and thank you for joining us in this live webinar presented by the Swarm community. This is a webinar series that is dedicated to covering different subject matter around taxonomy and ontology. We have the first webinar of this webinar series, Demystifying Taxonomies and Ontologies, after which we're going to cover enterprise use cases and methodologies on how to implement taxonomies and ontologies in the enterprise. With that being said, Michael, would you like to introduce yourself?
Absolutely. Hi, everyone. I'm Michael Andrews, and I'm a content architect and metadata consultant. I've written a couple books on metadata as it relates to content, which is very germane to what we're going to be talking about today. You can find those on Amazon if you're interested. And if you are interested in this topic, please feel free to connect with me on LinkedIn. As well. And we're very happy to have you joining us today. I know some of you tried to join us last week, and LinkedIn had a outage and right before we were going live. So we were very keen to present this material to you, and we're happy you've joined us. And I'm going to be joined with my co-presenter, Prasad, who is going to introduce himself.
Thank you, Michael. I am Prasad Yalamanchi. I'm the founder CEO of Lead Semantics. It's the developer of a product called Text Distill. As the name suggests, it's focused on distilling knowledge from text. I have a background in computer linguistics and knowledge-based systems development, machine learning, and so on. Most recently, over the last 4 or 5 years, through my team and with the company, we have been focused on knowledge graphs and large language models and such. And ontology is part of what we had been working on. And so that's pretty apt subject that we figured we'll be able to contribute to the community here. Those that are interested in catching up with me, I'm at the LinkedIn that is shown here. And thank you all again for joining us. I know we have kind of postponed it from last week, but glad you're all here. Back to you, Michael.
One quick thing. I don't know why I blanked out as soon as I turned on the session, but we were jokingly saying that we might have accidentally crashed LinkedIn. So apparently there's so many taxonomists and ontologists enthusiasts that we just flooded the LinkedIn platform. Back to you, Michael. I'm done with the corny joke.
Okay. All right, so I'm going to be talking about taxonomies, and let's just start the conversation by thinking about what taxonomies do for us. And they help us sort things, and we sort things all the time in our daily lives. An example of that is we sort our trash. We designate some things to throw away, and other things can be recycled. And when we decide what can be recycled, we may have to sort it further. What exactly is this thing that can be recycled? So we get into issues of like, we have a can. Is it a steel can or is it an aluminum can? We may need to sort those separately depending upon what our process is here. And what I'm trying to do just with this simple example is indicate that there are several different kinds of decisions being made here. One is, what categories are there? Why do things belong to one category versus another? And then what are the consequences of that decision about what category we place something in? So if I sort something incorrectly, if I put the tin can in the aluminum can box, what happens to that can? Does it get recycled? Does it mess up something else? There are consequences to sorting things. So if we look at the next slide, we can think about all the digital content that we encounter. And it is growing in volume all the time. So we have all kinds of texts that we read, not just web pages, but chats and emails and legal documents. We have data of all kinds. We have specifications for products and records of transactions, financial reporting. We got to categorize all this stuff. What is it? And then we have all kinds of media now, images, all kinds of recordings being made of videos and audio. And that needs sorting as well. We need to categorize that. And that's really what a taxonomy helps us do. So if we go to the next slide, a taxonomy, and this is a standard definition of a taxonomy that was developed by the ANSI organization. It's a standards organization. It is a collection of controlled vocabulary terms organized into a hierarchical structure. They go on to say that each term in a taxonomy is one or more parent-child or broader and narrower relationships to other terms in the taxonomy. Let me just unpack this a little bit and highlight a few of the key terms that are being used in this definition. First off, it's a collection. So a taxonomy term really doesn't mean anything except in its terms of its relationship to other terms. It also, the definition notes that it's a controlled vocabulary. And what that means is that it is a set of terms that have been standardized. We're not just using different words at different times that mean the same thing. We are standardizing what term we're going to use to represent this in the taxonomy. And then the final concept that I want to highlight here is that it's a hierarchical structure. The definition here talks about broader and narrower relationships. And this allows us to see what the relationship is between something in the taxonomy and other things in the taxonomy. I'll show you some examples in a moment. If we go to the next slide, I want to, though, broaden this definition a little bit. I've given you a very standard definition that's been in use for at least 15 years or more. But that's sort of a traditional definition. We want to think more about taxonomies as the structuring, the classification of concepts. And this is much more of a sort of semantic way of thinking of taxonomies around concepts rather than simply terms being used. And a concept is a very broad idea. It's about any object out there, any process out there, quality out there. We can classify concepts of all kinds. Next slide. Here's an example of how we classify concepts and how we use taxonomies. And it's going to be a simple example, but it actually represents some things that sometimes people find a little hard to understand. A taxonomy can classify a couple of different levels of detail. First, it can classify classes of things. So we think about modes of transportation. We have vehicles and we have cars. And so a car, for example, is a class of objects. There are many cars out there, many individual cars, and they all share certain characteristics. They all have, for example, 4 wheels. And then a car is a type of vehicle. And we make some assumptions about what a vehicle is. It's a mode of transporting people or goods. And we're going to assume this vehicle moves on land. I know there are amphibious vehicles, but most vehicles that people use will move on land. So we say that the car is a type of vehicle. And this gives us a sense of a hierarchy between these different classes of things that are out there in the world. However, there are many individual cars, and even though they all share 4 wheels, they have some distinguishing characteristics, say their paint color. And we can use a taxonomy to help identify some of the distinguishing characteristics of a car. So we can look at have a taxonomy of paint colors and say that, green is a color, and we can break that down further and say like neon green is a type of green, and use that to define a specific car, my neon green car. That specific car, my neon green car, is a car. It's an example of a car. So we see that's an instance of a class. And this is another use of a taxonomy, is it helps us identify instances of things as well as to organize classes of things. I'll touch on this a little bit more later on, but this is an important concept here. Next slide. So here's an example of a taxonomy. And this comes from something called the IPTC. It's an organization of media companies like New York Times, the Associated Press, BBC, Bloomberg, all members of this IPTC. And they have a taxonomy for news. So any news article can be categorized into one of these categories here. And they've made some decisions about what categories are important. So say something like labor is distinct from the economy, or society is different than lifestyle. That's decisions they've made about how they want to categorize things. If we look at the next slide, we'll see another piece of this. And it's the same taxonomy, but now we're drilling into some of the detail, and we're starting to see this hierarchy that was mentioned. So this part of the taxonomy deals with the economy and business information and different kinds of financing. And we can see that we're getting more and more specific. The terms are getting narrower in their meaning. And so this is how we get more precise when we're talking about what is being discussed, by looking at a taxonomy term. And then you can look at it more broadly. Now, you see here, there are two columns in this taxonomy. And when we talked about the ANSI definition at the beginning, we just were talking about terms. But on the left-hand side, we have a column that has a bunch of codes. These are what they call a media topic ID. And this is how modern taxonomies are constructed, is that they have both an ID and a label. So if we look at the next slide, we are thinking about how we're organizing concepts. And each concept that we have, we give it a label, a term, that controlled vocabulary that we mentioned, as well as giving it a very unique identifier. And the reason we do that is that machines really prefer an identifier. It just makes it a lot easier for them to process taxonomies, whereas humans, we don't really like ID numbers as much. We like labels. So we depend on these terms to unambiguously communicate what that concept is about. Next slide. Here's an example of how we can use a taxonomy to categorize content. And I've just taken a screenshot of an article from a business publication. And the article is talking about a company that is looking to split apart some of its business. And the article goes into the story about why it's doing that. And it's a bit of a business drama. It's not quite Shakespearean, but there's a lot of drama going on here. We have a company that's splitting apart because it was trying to actually merge with another company, and that merger didn't work out for them. And then later on, it talks about how it had acquired another company a few years earlier. And then the article mentions that the company it was hoping to merge with this time was a manufacturing partner of theirs. Okay, a lot happening in this fairly short article here, but we can use the IPTC taxonomy to start identifying very specific things being mentioned in this article. So we have a spinoff being mentioned. We have a merger being mentioned, a merger that might have taken place. There's a discussion about an acquisition that happened. And then there's this mention of a manufacturing partner. Now, I don't know if that's a joint venture or not, but we could check that out and see if it was. All these concepts are part of the taxonomy, and we can identify on a sentence level what is being mentioned in this article. And then also we can roll it up and know that this whole article refers to business restructuring for this company. And that's really useful to us. Next slide. So a bit more about hierarchy, because it really is the important organizing principle of a taxonomy. So we have a hierarchy of terms. And this is something you often will see. You'll see that these different levels being indented in different ways. And you can see the hierarchy as you're moving, getting more narrow as you move further in the indentation. Some of the ways we talk about the hierarchy of terms is we often talk about a root term. Each root maybe has some branches underneath it, and any specific branch can be a parent to other branches. So in this example, we have marine insurance as a parent to some other branches that are called children. So marine insurance has some narrower concepts. We have hull insurance, cargo insurance, protection and indemnity insurance. And these are all at the same kind of specificity. So we talk about these as all being children of the parent. And all these children are sometimes referred to as siblings of each other. Next slide. But I mentioned that we're not just looking at terms, we're actually thinking about concepts here. So if we think about this more conceptually, what we're looking at is we're taking types of finance, and then we're breaking that down, looking at types of insurance and types of marine insurance. So we're looking conceptually at concepts that will have common properties among them. We then know, we can think about things that belong to that concept as sharing these properties. Next slide, please. Now, hierarchy is something that allows us to say things about things because of the relationships that they establish. So it's more than just indenting things in a list. I know sometimes we assume that something is going to be narrower just because it's indented, like it's as though we're just talking about an outline for some article we're writing, but it's more complicated than that. And there's a test for hierarchy. It's called the all and some test. Now, on the left-hand side, we have an example of a hierarchical relationship. So we have birds and parrots. And how are they related? Well, we can say that some birds are parrots, and all parrots are birds. And what that means is that parrots are children of birds. We have properties of birds. Birds have feathers. Because parrots are a child of birds, we know that parrots have feathers. It just follows from that. On the right-hand side, we have a situation that's not hierarchical. So we have pets as a category, and we have parrots as a category. We can say that some parrots are pets, and some pets are parrots. It's not a hierarchical relationship. We certainly know that pets have owners, but not all parrots have owners. So it's not a parent-child relationship. Next slide. So what taxonomies allow us to do really is to classify things into categories, and they will allow us to think about what these things have in common. And we often approach this by doing sort of a bottom-up process where we look at something specific and then we think, what is this an example of? What kind of thing is this? So for example, a leveraged buyout is an example of business restructuring. So business restructuring is the bigger concept, and leveraged buyout is an example of that. Next slide. One of the ways we do this is to think about different ways of organizing things into categories. So we take something, and what category do we put it into? I've mentioned already one of the more common ones. We can look at generic relationships. Something is a type of something else. That's a very powerful way of doing it, but it often requires us to think a lot about what conceptual similarities there are between things. Sometimes we can get a little bit more specific. There are what are called whole-part relationships, that something is a part of something. My arm, for example, is part of my body. We can think about the uses of things. Sometimes if something has a very specific use, we can say that something is used for something else. By composition, something is an ingredient to something else. And as we mentioned with the neon green car, there are instance relationships. Something is something else. Microsoft is a company. Microsoft being an instance, company being a class of things. Next slide. And really, I want to encourage folks to think in terms of the categories themselves. So there's often the tendency to want to think about the words you're going to use in your taxonomy before you've sorted out what ideas you need to classify. So if we start with an idea about something like a change to the structure of a business, that's a very important idea. If you're an investor, you want to know about changes to the structure of a company that you've invested in, or if you have a competitor who you need to pay attention to, you're going to be very interested in any changes to their business structure. But then you say, well, what does that really mean? And then you can start to enumerate different ways that a business their structure could change. It could change because new company has been formed from an old company, or companies getting together in some way, or changes in the financial composition of the company, or two companies forming a venture together. When you enumerate these different ideas, now you start to see the relationships between something narrower and something broader. And when you're comfortable that you have these things and you say, all right, now I have a clear sense of what I mean by this broader concept, and I have these narrower concepts, and I can see these are distinctly different concepts. They're not bleeding into one another. They're distinct and different. Then we can, in the next slide, think about how we label these things. And labeling can change. We have some opportunities to do that. We always want to use a consistent label at any given time, but we can change those labels if we need to. But we want to have the concepts very clear in our mind, what it is that we are looking at. So then we say, all right, this is all about business restructuring. And we decide on these labels of a company spinoff or a joint venture or a leveraged buyout. These are shorthand for the concepts themselves. They stand in for that concept. And hopefully communicate what that concept is, but the concept is going to contain more detail than the label itself will say on its own. Next slide. So a couple of bits of advice around labeling. It is really important. This is how we as humans interact with taxonomies. So we want to have labels we understand. We want to avoid, say, jargon that's outside of our comfort zone. And so the best way to do that is to use common, readily understood words rather than, something that's going to look, unintelligible to us. But having said that, we also need to be aware that sometimes common words can be ambiguous because these words may have more than one meaning, or they maybe are just a little too loose. And so they're not precise enough to help us really nail down what that concept is that we're trying to label. So we need to be aware of that, use as the most familiar words we can, while at the same time making sure that it's not introducing any ambiguity. Also, got to acknowledge that we are standardizing on one specific label, but we don't expect that the content itself is always going to be using that term that we're using in our label. And that's fine. The label is there for the purpose of the taxonomy. It's not there to try to make the content say something that it's not saying. So we will expect there may be different spellings associated with that term. There might be acronyms or informal terms or synonyms being used. We can make notes of that and connect those other expressions to our label and connect it to our concept. But when we're navigating through our taxonomy, we're going to have this controlled vocabulary term. And then one more slide here. The benefits of doing this. We are standardizing how we talk about concepts. And this gives us several benefits. One is it's disambiguating things. We're not using different terms or using the same term in different ways, or maybe using different terms to mean the same thing. We're standardizing on things, and we're as a bunch of users in an organization, we all clear what it is we're talking about. We're able to summarize very succinctly what's happening in some content. So we think about that article I showed you. Those terms, when we said, a joint venture, a merger, those are very succinct ways of talking about what's going on in that article. And lastly, we're normalizing how we're talking about things. So different articles are being produced by different organizations or different authors. They may be talking about things in different ways. They may be using different terminology. They may be sometimes in different languages even. But with the taxonomy, we're able to use a standard taxonomy and be able to describe what's happening across different pieces of content. And this allows for interoperability. We were able to connect things that are using different words or talking at different levels of detail and connect these things so we have a sense of what's going on with them. So it's tremendously valuable, and it becomes even more valuable when it's connected to the other tool we're going to talk about today, which is ontology. So I'm going to turn this over to Prasad now, and he's going to help demystify what ontology is about.
Thank you so much, Michael. That was clearly eye-opening on some of those slides, what you talked about. And to all the participants, welcome to the second part of the webinar today, which is demystifying the ontologies. As Michael mentioned at the outset, this is the complementary technique to handling information and managing and organizing knowledge. Yeah, next slide. So I will start off by beginning where Michael more or less kind of mentioned, which is the part of taxonomy which is dealing with concepts, is where we pick up here in ontology. And hierarchy was one of those ways that relationships were helping expand on the meaning of what a concept was from the point of view of a taxonomy. We will take it much further when we are dealing with ontology. And so that sets me in setting the stage for what an ontology is. It is a semantic model of any domain, knowledge of a domain. And when we say semantic model, it is a model based on meaning. And we'll have a chance to talk about, what a real meaning is, even though these words are kind of used on an everyday, every hour basis. But there is, we can dig it a little further to kind of give us some basis for what these things really are and how they help us organize information. So ontology models, they are representing a domain or a subject area by identifying and expressing unambiguously the concepts, that form the metadata of that domain. So if you have a domain like finance, as we mentioned here, the core concepts are unambiguously modeled, and we will get into how some of those things are actually done through this technique called ontology. The central concepts, for example, in the domain of finance is like a company, a trade, a stock. For example, we are all aware of it. And so these central concepts, once you give it a representation in the ontology, they become the metadata of the ontology that allows for you to take the instance data that is pertaining to this domain, and then it gets organized into this knowledge driven by this ontology or powered by this ontology. Some sample instance data. Microsoft is a company. That is an instance. It's an instance of a company, an idea called company, or a concept called company. And it has a stock label called MSFT. And trade, for example, I'm giving examples to what we talked about as central concepts here. Buying Microsoft 1,000 shares, so that's a trade, for example, and it has a label. And so that is an instance data, and that can be tracked through all of our electronic systems and so on. And a sample ontology, for example, since we said it's an ontology, is a model. I'll start by mentioning SKOS, SKOS. It stands for Simple Knowledge Organization System. Michael mentioned, organizing concepts and the taxonomy itself using narrower and broader concepts. While taxonomy is much more of how you organize all of these things, you can put it into a machine understandable format by using this ontology called SKOS, for example, the Simple Knowledge Organization. And more fleshed out ontologies are there, more deep, and all these relationships that go beyond hierarchies. And ontologies are meant to handle all of the relationships that are pertinent to capturing the core essence of the domain that you're dealing with. And FIBO is one of those. It is financial industry business ontology is what it is. And one of the big use cases that it is getting really a lot of wind these days, and it has been in the last decade or so, is a knowledge graph. Knowledge graphs in an enterprise are becoming very important. They have been around for some time, but they are getting a lot more attention even in the world of LLMs have shed new light on it and so on. And ontologies are an important ingredient, necessary ingredient to build proper knowledge graphs. Once you build a knowledge graph, the right-hand graphic is kind of give you a sense of what some knowledge graph would be. A snapshot of a knowledge graph in an enterprise might look like. Next slide. Okay. Yeah. So we mentioned semantic modeling, and so semantic modeling has been around, and folks in the IT industry have been exposed to different types of modeling and so on. And so semantic modeling is one other technique, one other way of modeling the domain. Two other important modeling techniques I would like to draw a contrast with semantic modeling is relational modeling is one of those. And the other one is object-oriented modeling. Relational modeling, it is focused on entities and relationships, and it is powered by the relational algebra. It has a very sound mathematical basis for it, but it targets a different type of goal. It is much more transactional handling, and also it reflects the technology of the time when it was originally invented. And so relational modeling allows you to model entities and relationships in the form of tables. A table is like one single entity, like a car, for example, and all of its attributes would be other attributes in the table, other columns in the table. And then if a car has a relationship, of course, with its driver and so on. And so driver is another entity, and so that would be another table. And so if there are multiple cars in a table, then so you have unique identity and so on. So that is the basis of what a relational modeling would entail. And it's markedly different than object-oriented modeling, which is kind of a much more recent than relational, for example, and it is centered around abstraction and encapsulation of information. So when you have an abstraction called a car, all the information, all the attributes are related to a car, for example, should be one abstraction. And so you talk to it as if it's a real entity, all of it put together with all of its attributes. And so it has implications on how the memory organization in the computer and all of that. So it has a target of a different kind. It's much more of enterprise, big systems development and so on. Of course, there are later stage developments that have kind of have all kinds of opinions about how well it was able to handle complexity and so on. But the necessary characteristic is that there are objects and then pointers from one object to another object whenever there is a relationship that it needs to track. But there is the primary ownership of attribute to a given object and so on. And so that is the object-oriented modeling. In a nutshell, we are not getting into full detail here. So in contrast to that, semantic modeling is about entities. And of course, we are modeling something that is of importance always. I mean, of course, a relational, object-oriented, or semantic, it's always of a domain of interest or an application you're targeting towards. But the motivation for semantic modeling that is necessarily a little different than other modeling is that it is rooted in being driven by real-world, implications, or rather real-world motivation. If you are talking about a car, for example, and you are trying to model, you are not necessarily limited to just a car. You are talking about the subject area of something like maybe it's a traffic system, or maybe it is ownership, or some such thing, a broader area within which this particular concept that you're trying to model has a place in it. And now you are trying to draw all kinds of relationships to other real world entities that naturally have relationships to this entity that you're looking at. So the motivation is driven by what the implications are on the concept that you chose from the real world. And so it's a lot more independent of the systemic view that relational and object-oriented modeling kind of limit. I wouldn't say limits you to. Rather, it kind of it lets you go by with a systemic view, the data that is available to you in the enterprise, the data that you're looking at, the things that you have looked at. Whereas semantic modeling kind of drives you to put it all the way to the real world. And there are far-reaching implications of that seemingly simple thing that we tend to always, just overlook in our conversations and things like that. We understand each other because the things that we say are rooted in the real world. That's the real basis for it. Are things that we have already negotiated to be the common thing that we agree. It's that kind of a common thing that drives the modeling of, this type of semantic modeling. And the same entities and, the same entities will have properties and its relationships. The way it manifests in a computer-based anything is a statement, much like a language, it's a statement. And the anatomy of a statement is a triple in this case. And a triple is like two nodes connected by an edge. And I have these examples here. You have person 32. Person 32 is like an ID of some person who is working for a company 71, another instance of a company. This person has a name, John Doe in this case, and the company has the name Acme Inc. So each one is an edge, that is connecting two nodes, and edge has the name, and that is the relationship. That is the entire format that you would have to keep in mind. But it is, as you can see, it really tracks relationships between entities. So as long as you have an identity of something, and of a relationship that is rooted in the real world, it's a lot easier to kind of verify, where you are with the model. That is semantic modeling. based in the real world and the meaning in the real world. Yeah, next slide. So we are talking about this meaning, and so I figured I do want to kind of bring in this rather abstract slide, but I think it may be necessary. So modeling the real world through semantics means that you are modeling through the meaning, and meaning of anything we take is the constituents. I mean, this is where it gets a little bit abstract, but I'll try to kind of unravel it, hopefully. Of anything is the constituents of the meaning. And of anything is the constituents of the relevant, some reality, the meaning of some reality. We said, reality, the meaning of some reality. Whatever is that reality and the constituents of that reality form the basis for this meaning. And so that is what will drive us to kind of, come up with how you draw a reference between some symbolic mentions, like, for example, in this case, a tree is something, as you see in some mention in a content, in a text somewhere, you see the word tree. How does it connect to the actual tree? So the tree is recognized, or at least it's kind of it's known in our minds. It symbolizes for some ideal tree, the concept tree. So a concept itself is like an idea with a definition. So we know, with our prior past experience or prior agreement in a community or whatever, the definition of a tree is, such things as we see that are green and with a root and, so on, right? And so when we see a symbol tree in a content or in some article somewhere, it kind of symbolizes for us this idealistic tree in our minds, and that refers to the actual tree that we may be seeing. And so that's how the symbol that we have seen is actually standing for the real tree that we may be seeing. So that is, it has its own name. It's a semiotic triangle, but as an introductory class, we do not want to go any further than that. But the most important thing is that the content, the tree, which is symbolic, how it connects to the real world reference, right? And because that is the meaning ultimately, right? The meaning of tree is what it is in the real world, we said, and that is the rule and the basis for our modeling, we said. And that technology is semantic technology. It structures these constituents of this reality into machine understandable data, which are these objects and properties and relationships. That's how semantic technology has the basis in this, how the actual symbol is connected to the real world through our mental models. And so semantic technology is what drives semantic modeling. Right? Yeah. Next slide. And so semantic model is the ontology, and it comprises of, we said, the core concepts of a domain, the core concepts, and then the individual things that, that can be categorized to these kinds of things, that reflect the concepts of the domain. For example, the kinds of things are like companies, and so they will be called classes. Once we are getting into an ontology, now we are getting into a little more formal terminology of a modeling language. Yeah, so these are classes. So a company is a class because there could be many instances of companies, like Microsoft, for example. That's an individual thing. An individual thing will have its own name, Microsoft in this case, and it will have its own individual identity, and right, like some kind of a unique identifier, whatever that computer really would like to, as Michael has alluded to. And now with kinds of things and individual things, you are starting to relate to things in the real world, and you are able to give it a definition, like a class and so on. And I picked up this graphic from Michael's slides here. As you can see, the neon green car is an individual instance. It is a car, so it's an instance of a car, and car is a type, which means a car is a class of vehicle, when we come into ontology. That's how taxonomy has a direct handoff into ontologies. And so that is where, these are two complementary things, if you hadn't already noticed that. And The triples, as we mentioned, are in the format, as we said, there are two nodes and one edge, and the two nodes have a distinct role to play in that, that edge, or so-called the statement. It's a subject relation to an object, that is the triple, and the relation is called a predicate, and so things in the real world have attributes, and these attributes have values, and things have relationships to other things, and they form these triples when you try to model it in an ontology. And the classes and terms are from the taxonomy of the domain, right? And so it's a natural, hand in glove fitting into, what we have to do in ontology, coming from taxonomy. Next slide, please. Yeah. So now that we are firmly into the land of ontology, some sample triples here. We talked about Microsoft as a company, and Microsoft here, we talked about triples, some sample triples here. Microsoft is the subject, and the relation is headquarters in, with an object called Seattle. So Microsoft headquarters has headquarters, however you want to read it, but the format is that the middle thing is the relation or a predicate. It is connecting subject and the object, as you can connect it to the graphic on the right hand side, subject, predicate, object. And then the bottom arm of this picture, subject, predicate, and a literal, is, for example, I can highlight that in the second statement here, Microsoft founded in year. Founded in year is the relation or the predicate, and it's connected to the string 1975. So 1975 is the literal. It's not an instance of a class, even though it's an instance of a different class altogether, but it's the literal value. There is no other meaning other than 1975. It cannot stand in for something else, right? And so it does not have any additional properties other than what it actually purports to, mean to you when you look at it. So that is the literal. And Microsoft has partnered Intel in the last statement, so that's what it is. And ontology as a modeling language is actually rooted in standards, and so that is one of the benefits of, besides the actual conceptual, way and the power of capturing the real world in terms of what computers can do with that real world models. Ontology is actually based in standards, and the modeling language is called OWL. It stands for Ontology Web Language. It's called the semantic web language as well, semantic modeling language, and it's part of the semantic web standards, and it has a big history, maybe more than 2 decades, and the central part of this OWL is how we give a standardized label that computers can actually understand, or rather, can index. It's called RDF. It stands for Resource Definition Framework. Between RDF and OWL, these are like rooted in semantic web standards that gives power to the semantic way of modeling a domain. And later on in the next slide or so, I will tell you what is this semantic modeling will give you besides actually modeling the real world. It is making the real world, once it is given the body in terms of these standard statements and standard language of the standard, it is actually machine understandable. Much like humans will understand, machines can understand as well. The same thing that is, modeled in here. For example, here we'll start with instance data, some simple example, the same examples we were looking at. Microsoft as a partner, Intel, we said. Microsoft is a company, we said. And Intel is also a company. And Microsoft is headquartered in Seattle. And Seattle is the location we know. And so when we say Microsoft is a company, the standard OWL support for it in terms of the language, the modeling language, is this the predicate that you see, the relation. It's called RDF :type, or it reads RDF type. These are like standardized labels, terminologies of the OWL language itself. And these are, as you can see, the headquarters in are located in, or if it has that, right? So those are domain-specific relations, whereas these are modeling specific, relations and predicates. And this is how you actually capture the instance data of the real world. So there are classes, kinds of things, and there are instances of things like individuals in the real world. Like Microsoft Seattle, Intel, and Santa Clara. Location and company are abstract, and these are like classes. Yeah. Next slide, please. Now we have seen the instance data, how OWL will give you support to model it. Now the metadata of the same piece of knowledge, like company and its location and headquarters. If you look at the abstract aspects of the knowledge that we had seen in the prior slide, which are company and location, which are the two classes. And so company is of type OWL class, so that's again, meta data within OWL itself. So that supports creating classes and making known that, this is a class, so that it is available to be used in assigning individuals to that class. Like, company has a partner with another company is part of your domain model. It's not part of the OWL model. So OWL model is talking about classes and, so how classes interrelate to classes at a meta level. Whereas companies and locations are real world entities, but abstract ideas of the real world. And then within them, there are relationships. And how do you model them is using the same OWL language. This is how it appears. So this is the metadata of a specific piece of domain area of some knowledge. Yeah. Next slide, please. So with that, so because this is a high-level introduction of what ontology is, it gives you that rigorous way of modeling real world in the context of your enterprise applications. And in doing so, it's also making it machine understandable. And there are enormous benefits of making knowledge machine understandable, because knowledge is the highest level of artifact, if you will, in the intelligence pyramid and all of that, where you have data at the bottom, you have information, and then knowledge is at the top, and intelligence is the one that kind of drives these things up the pyramid. And so the goal of any enterprise or any activity with information is to reach that end goal of handling knowledge. Of course, as humans we always do that, but making machines do that. And I will so with that I will kind of get into the slide of motivating why ontology is important at this day and age. One important thing is it unambiguously communicates knowledge. In doing so, it's also making it machine understandable. That's pretty significant. And ontology models knowledge, as we said, not just information and things like that. And pieces of information add up to knowledge, and so but it's modeling knowledge all the way. And it is rooted in real world. And because it is rooted in real world, the serious benefit of that is that it becomes an easy basis for integration across these models that may be developed by different groups, different departments within the same company, maybe different companies even. As long as they are dealing with a similar domain or a subject area, there is a good chance that the integration becomes easier, and especially if they are using ontologies and such. And there are actual practical methods. This is the best known technology to integrate in the cheapest way possible. And we know historically integration is a very expensive proposition in companies during mergers and whatnot, and even across developments within the same company. And the third big benefit is it is rooted in standards. So that is a huge benefit. And more importantly, it is not only standards, just that all the big names, big people have got together and standardized. That's not the only thing, but big people have gotten together and made it rooted in formal logic. So in other words, it's unambiguously you can prove that a model is verifiable or not. And that leads to machines inferencing new knowledge, for example. Either it is inferencing new knowledge, or it may be inferencing to point out that your model may be wrong. Both of which are extremely valuable. When you go to these abstract things called knowledge, right? And so the value add is tremendous. And the third one is that, as I mentioned early on, you can build knowledge graphs with these ontologies. And enterprise knowledge graphs have proven to be extremely valuable. given that they were expensive all along, but now not as much, with the advent of LLMs, and I'll speak about the benefit of that along the way. And knowledge being that it is machine understandable, it allows for automated decision support, unlike any other technology. Because any decision has to be rooted in complete knowledge that ought to power that piece of action or a decision. And so if knowledge is machine understandable, then it leads you up to, a possibility of, making a decision. Automated driving, for example, extreme pains are being taken to kind of, procure and bring up all the knowledge to the point of decision, maybe doing a right turn, left turn, whatever. It's always that complete knowledge to do that action has to be available at the point of wanting to make the decision. And so machine understandable knowledge is a core component of that. And another important thing, and it is a very case in point to what Michael has been talking and what I'm continuing to talk on, is the content. A big part of that is unstructured text. It is laden with knowledge, and all that untapped knowledge can be added to an enterprise knowledge graph. And you can imagine all of that not only can be searchable by humans and so on. Now, given that if it can be added to a knowledge graph and it is, it can feed into automated decision support, the decision support has now become that much more richer, the environment, because text historically has not really played a big part in the knowledge basis of the company, other than directly to the humans. And ontologies, by extension knowledge graphs plus LLMs. I mean, we cannot talk anything without talking about LLMs and generative AI. And ontology is a nice complementary technology to generative AI and LLMs in that. And there are groundbreaking possibilities that kind of abound, actually. Being in this space as a company, we are exploring these specific use cases. One of the big use cases, ontologies ground LLMs in terms of controlling their hallucinations. Because ontologies are rooted in knowledge that is accepted by a community and so on, and these are concepts that are well rooted in real world, implications and so on. So they have natural, guidelines to control hallucinations, and practical examples, and we have our own product kind of does that. Focus LLMs, and the other thing is ontologies focus LLMs to a domain, because that's another downside, or rather inadequacy of an LLM, is that it cannot control itself to a specific domain. It knows so much, being that it's trained in all of the text in the world and everything there is in the world. It doesn't know where the bounds are for a given domain. But if you wanted any real world practical application, it's domain specific. An ontology can, ground it, focus it to a particular domain. In that sense, it not only has the potential to reduce, it can possibly eliminate the need for fine-tuning LLMs, which is a very expensive proposition, given that these generative AI models are so big and they require these GPUs and all of that. And then they still continue to have these, inadequacies kind of, continue on, these hallucinations and lack of this domain specificity. With an ontology, you have now the control of guiding an LLM to, what your domain specific intent is, and what you are looking out to make it deliver. And this is another thing I'll have a chance to talk about in another webinar, I think, is driving complex workflows with LLMs. The LLMs are like, digital minions. They can really be used to, serve your needs and so on. They keep generating as the next thing and so on. But last thing you want to do it is buried in a complex multi-segmented workflow. One piece of a workflow handing off to a next segment in the workflow as the result of an LLM output. You cannot do that, because what if it hallucinates and it produces something that the next segment will crash, or does something completely adverse to what you're looking for. Whereas an ontology can constrain it, as I said. And that is one of the biggest possibilities for end-to-end automation that can drive down these LLMs deep down into complex workflows. Of course, a lot of these things have to be grounded and then tested and so on. And the other immediate thing, upgrade so-called this popular RAG system that's so popular, widely popular, retrieval augmented generation, that is, constraining LLMs to a particular domain in the sense of, limited set of documents, for example, of a domain. It has shown that it does very well over and beyond a regular LLM in answering questions. Whereas with the RAG, there are still certain problems in terms of all the known problems. I do not want to go into all of that, but it doesn't traverse the connections. Connections are such an important relationships to entities that are important to your domain. Your questions, for example, are very important aspect of it. And if these relationships lead to other data or other concepts, you do want to explore that if it is a candidate for an answer that could be a candidate for your question that may be asked. And RAG would not get you there. And so that's where graph RAG systems really fill the gap. And there are other issues with the RAG system. It doesn't go all the way. And graph RAG is the next big thing. Even recent Microsoft research paper kind of alludes to that. And so these things are possible with ontologies, clubbed with LLMs. And so now ontologies and knowledge graphs are prime and center, in the world of LLMs. And that's the benefit that you can really start to aim for when you get into these ontologies. With that, I will close. This is the first demystifying at this point. So I'll leave it back to Joaquin.
Michael and Prasad, thank you for that thorough demystification. I certainly feel slightly more demystified, if that is even a word. I want to take note that the next webinar we're going to be holding is on March 20th. We will be covering enterprise use cases of taxonomies and ontologies. In addition to that, we also have some programming for an event being called the Data-Centric AI Forum. And yeah, we welcome you guys to just check out any more events that are coming out of the Swarm community. We're going to transition now into the Q&A portion of this webinar. We have approximately 15 minutes allocated for that. Any more questions, and you could just leave us a comment. We'll see to it that we can go in and answer them as we have capacity for that. I do want to just take a plunge here to see if I can encapsulate this webinar into a 1-minute summary, and then I'll let you guys beat me if I'm horribly wrong. But let me start by saying taxonomies and ontologies are two complementary knowledge organization systems we can use for human-machine interactions that support the transportation of meaning and context between actors being human or machine.
Yeah,
so far,
I would say so far so good. Yeah.
And these knowledge organization systems help us document explicitly, understand the relationship between, and reason with different levels of meaning. So this extends from concrete being a green neon car, Volvo, to car or vehicle or transportation module.
Yeah, I think that's a really important benefit of this, is that we are able to speak both to very specific things as well as to more abstract things, because I know abstraction can sometimes get a little mind-numbing. Our brains don't really enjoy abstraction all the time. I mean, but abstraction gives us the capacity to generalize about things, and that's really why humans evolved to conduct abstract reasoning. And what we're allowing computers to do is abstract reasoning as well. I mean, computers have been very, very much about just collecting lots of details and aggregating them, but not necessarily abstracting them and coming up with sort of broader conclusions about things. And so I think, taxonomies in the first instance and ontologies in the second instance are allowing computers to do more of that abstraction and to get those sorts of insights, and then we're able to actually drill back down into very specific things based on having that. So just to preview, I mean, we can ask any answer any specific questions people will have here, and they're welcome to drop them in there. But we will in our next session be getting into some use cases, which I think will help to make a lot of this more concrete. Because right now we are talking a bit theoretically, and I understand that some people may still be wondering, well, how does this really get put into practice and all? It's great to know that there are these trends out there, and this fits into the trends, but how might this really be useful to me individually or me, my organization? And so we'll be getting into a little bit more of that in our next session, which is going to be a week from today. Just wanted to plug that in. Sorry to interrupt you, though, Joaquin.
Marianne Sweeney, she said, could they be seen as a lingua franca between humans and machines regarding meaning?
I think it's a great way to look at it. Absolutely. I mean, it's important to recognize that humans create the ontology, right? I mean, we all, as Prasad was mentioning, these are standards, and these are collective groups of people who are deciding, what's in a domain, or or on the more abstract level metadata, what are these conceptual relationships between things, and we come up with an agreed definition of what these things are. It makes sense to us as people, and then we've developed these things in a format that machines can ingest and process and do things with. So it is a lingua franca, and I think compared, and then I'll just backpedal and say I come from a background in human-computer interaction, so this is very close to my interest personally. Is finding ways for people to interact better with computer capabilities and computer data. And one of the most exciting things about the whole area of semantic technologies and knowledge graphs is that it is understandable to people once you understand the basic mechanics of this. We're using words that we can readily understand, but they're also understandable with machines. So it's really great.
We have another question from Mike Bennett. Have you looked at the OntoClean methodology, Guarino and Welty? This applies many of the same important principles that Michael described. Hi, Mike.
I'm not personally familiar with the OntoClean methodology, but yeah, thanks for pointing that out. I'll definitely want to take a look at that.
Yep. Hi, Mike. Yeah, I'm not aware of OntoClean. I definitely would love to look that up. Yeah.
We'll have to get back on to you on that one, Mike. But I do want to point out that in this it's kind of hard to see, as you were saying, Michael, how you apply this in practice. I mean, we gave a few very cute examples, right? I mean, neon car, vehicle. But if you look at car is a complex piece of machinery that has many hands, many brains touching it. I mean, you have wheels, you have axles, you have the gear systems, the planetary gear systems, the engine, the oil system, the fuel system, driver navigation, seats, paint, materials. Yep. There's so many different subdisciplines, areas of knowledge that have to come together to build this one Volvo 2001 whatever. You really need to be able to orchestrate these in a complex maneuver, and what better way to do it than with a formal way of representing things explicitly, where we can put all of our knowledge in a pot in an organized fashion and then organize this very complex project in an efficient way.
Absolutely. I mean, and I think cars are a very practical example of how these technologies are being used. Is that as Prasad mentioned, the beauty of modeling real domains with ontologies and knowledge graphs is it allows you to connect anything that's relevant. We're not constrained by how we've defined a table or something like that with more traditional database approaches. And people are defining the bits and pieces of cars in ways that you can relate them together. There's a whole group of people who've defined a car ontology that's being used to define the characteristics of cars, and then you can relate those things to the sales of cars or the insurance for cars, and all the associated things that connect with cars. So it's very, very useful, and we obviously haven't been able to get into a lot of detail today on that, but I do want people to know it's highly valuable in a practical way.
One thing I would add, just to continue on what Michael is saying, is ontologies is also pretty interesting in the sense that it is a highly modular kind of a technology. You can develop ontology for body of a car versus an engine of a car entirely differently. Maybe it's a different group that is doing the body design and parts that go into a body versus the mechanics of an engine. On and on, like traffic. Somebody else is modeling. Maybe car is part of that as well. But all of them can still come together. And ontologies naturally have it, and it is inherently one of the biggest value, that because it is rooted in the motivation that you drive from the real world, there is that fundamental allowance for easy navigation between systems that may be developed by different teams. Mike has another question here. Yeah.
Well, it's more of a comment, but I think he's also pointing out the dangerous element of a general common word. Car can mean many different things to many different people. It could be a design, it could be a system, it could be an individual resulting product. And I think Michael said this very well. There's different organizational functions that a car can be seen through: sales, insurance, marketing, manufacturing, procurement of supplies from people that make the engines, or all the constituent parts. It's a complex web of materials coming together to produce a finished product.
It is, and I think just to Mike's statement, I mean, the ontologies I've seen relating to cars will define it as a product, so there's a whole separate ontology for cars that is a separate but related ontology to the schema.org classification that is a very generic ontology for things that we find on the web, but it goes into a lot more detail for cars specifically. And then there may be some additional ontologies out there, and this is getting a little beyond what probably most people would expect to know about. But one of the interesting things about ontologies is that you aren't necessarily restricted to just using one. You can actually use multiple ontologies, and as long as you sort of define that you're using several of them, you can take bits and pieces from different ones to meet your own purpose here. So that's another nice benefit of this.
Uday Gary?
Garvey, yeah.
Gary, yeah.
One of the key aspects that I understood is, with the help of taxonomies and ontologies, it helps us to organize the data in a predefined domain level structures model.
Yeah.
He goes on to say semantic models are giving structures to store and process data. Yeah.
Absolutely, yeah. And that's also a nice thing, is that there are, I think, a growing number of options for people to access this data. However, wherever it's stored, because we have these structures, and so it can be stored in different kinds of file formats or different kinds of databases. There's a lot of options, and this scales up incredibly well. So there's like no limit to how
Right.
big or small you can make this. It can be useful on a pretty small scale, but it can also go into just phenomenal levels of volumes of data.
And the other side is that given it is rooted in standards and like RDF and OWL and so on, and the serialization standard is part of what it is as part of your algorithmic processing as well. And that allows for really mixing, and the scalability kind of is inherent to the overall what you get out of this.
I'll throw a curveball into the conversation for Michael. Michael, how does the metadata hook into this whole semantic web of things?
Well, the metadata is helping us to define really the properties that we're interested in, and so metadata is in a lot of aspects of metadata sort of predate some of these developments, but then it's actually a lot of the developments have been built upon what metadata has been able to provide. So if you have a more traditional style of programming, you can still access this and just use these definitions as your metadata that would interface with a more traditional system. Just to give you an example, you can write this all as a JSON file, for example, and that's just something that any web developer would be using. They don't need to know any special database languages or something like that to access it and do things with it. But you can also just think about the formal ontologies as being a much more formal form of metadata as well.
And last curveball that I'm going to throw, and then if there's any last questions, this would be the last question. Prasad, how does metadata, machine learning, and ontology go combine to make a more cohesive pattern recognition solution?
Wow, I mean, you had to really cover it.
I was,
it's like a geodesic, I mean, let me parse it. I mean, metadata is ontology is the modeling thing, and then the core concepts of a domain, as we said, are the metadata within the ontology. So those two terms are kind of handled at that level, and there may be additional nuances to that. But the other one, because this is well organized data now, once it is kind of guided by an ontology, the data itself is a lot more, I would say, pristine data that can drive machine learning models for your predictions and so on. That you can reliably enhance your classifications and put a finger on, what kind of data would actually change the thresholds of the classification on the other side. So you get that threaded effect all through and through if the data is coming through a knowledge graph. And knowledge graphs are rooted in ontologies, which are kind of, the core conceptual models that are, handled through the metadata of the domains. That's how you can see them all, back to back.
So metadata lets you make shapes, lets you make more explicit shapes that show relationships between things. Those shapes make it easy for patterns to be recognized by machines. And as long as you hook that to an ontology and you create a knowledge graph, it makes it that much more complementary, as opposed to just having fragmented pieces of data that don't really have a shape, that can't really hook into each other, right?
So I mean, if I may take a minute, metadata is data about data, right? Information about how the data itself is. And patterns they exist in any bunch of data, any bunch of anything. As long as they're distinct, numerous things, there could be patterns that are there lurking around. Whether the patterns are desirable or not is dictated by the regularity of the data that you put in, right? And the regularity, you can aspire to that through the metadata and the ontology that you design for it.
Thank you for that answer. We have the last one, absolute last one. Alan, also thank you very much. Andrew Padilla says unified canonical models are a myth. I think ontologies recognize the domain-specific meaning of all things, in all its facets, and allows you to draw relationships as the needs arises without starting over. Hence, its integratability.
Integratability, Yep.
Great questions from people. I really appreciate everyone's
right.
comments here.
It looks like the attendees, the participants are already experts. I think we don't need to demystify anything to this audience, at least so far as the questions we had seen.
Be sure to tune in for the next one, enterprise use cases using taxonomies and ontologies. We hope to see you there.
Hope to. All right.
Thank you so much. I enjoyed it.
Thank you. Bye-bye.
Bye.